Hello students, this is Professor Chalai, and in this video we're going to look at mathematical treatment in chemistry. You can follow along with our chapter 1 worksheets. Now, as you've probably realized so far, there are a lot of math in chemistry. And in fact, you'll go a long way if you're comfortable solving math problems because a lot of chemistry problems can boil down to just math problems. Now, one good sort of tip to solving math problems is to uh, is to first sort all of the information you're given in a typical problem. So in a typical math problem, using these examples in your worksheet, they're often written in terms of sentences and paragraphs, but within those are the crucial information that you need to solve the problem. That's why it's important to read every problem very carefully and then pick out within those problems the things that you are given, pieces of information that you're given, and from those word problems, what you're actually asked to find. Because if you don't know what you need to find, then there's no way you can go about solving that problem. The second thing that I would ask you to do is form a strategy. Once you have the data that you're given and the data you need to find, come up with a strategy to get from the data that you're given to the data that you need to find. Strategies will vary from problem to problem, and there is no universal strategy. So this one is all dependent upon your creativity. There is no one way to skin a cat, and so there are many ways to solve any of these mathematical problems. Your strategy will depend on what you are comfortable with. The third step is to actually solve the problem based off of your strategy. Setting it up, going it over step by step, punching numbers into your calculator, solving the problem using your strategy. And then finally, a step that most students I think skip is to check your answer. Uh, Make sure that the units that you have for your answers match the units of the things you needed to find. If your units are different, then something may have gone wrong. Think about the magnitude or the size of your answer. If you're asked to find the weight of an elephant, but you got 2 grams, something went wrong somewhere because the number that you got doesn't match what you expect the answers to be. Not always are you gonna know in what ballpark your answers need to be, but oftentimes when you do, you just make sure that your answers make sense based off of that ballpark. Uh, and as I've mentioned earlier, dimensional analysis is going to be a very important tool in solving these mathematical problems. If you've remembered, we already went over dimensional analysis, but just to reiterate, basically you can do with the units the same things that you can do with numbers. So units work like numbers. That's all I'm going to say about dimensional analysis. So almost every number would have a unit, and you could use the units the same way you deal with the numbers. Let's go over some examples of how we can use sort of this strategy to solve some mathematical problems that would come up in chemistry. You can pause the video here and try number 26 by yourself first, but I'm going to go over it now. Okay, so in number 26, it tells us that the density of titanium is 4.51 grams per centimeter cube, and it's asking us what is this density in pounds per cubic inch. So first we need to figure out what information are we given and what information we need to find. And here it is. They need us to they give us the density and its units, and they want us to find a density in the different units. So that we need to find answers in x pounds per inches cube. I'm often going to use x because just in math, people use x to represent something that you need to find often. So we're just going to call it x pounds per inches cube. So this is what we're given. This is what we need to find. So that's the first step. We sorted the information that the question gives us. Now we need to come up with a strategy. So 4.51 grams per centimeter cube, and we've already done examples of this sort of problem, but we need to go to pounds per inches cube. In problems like this, we can use dimensional analysis to come up with a strategy. So the mass here is in grams, whereas the mass over here is in pounds. So we need a strategy to go from grams to pounds. Now, you may have remembered how many grams are in a pound. in case you didn't, 1 pound is 453.59 grams. But you might not remember that. But you might remember that 1 kilogram is equal to 2.205 pounds. That's one that I remember. And then that will help us get from kilograms to pounds, but we don't have kilograms, we have grams. So we should know that 1,000 grams is 1 kilogram. So that's a strategy. We can go from grams to kilograms and then from kilograms to pounds. So let's do that. We can go from grams to kilograms. 1,000 grams is 1 kilogram. Put it in the denominator so grams can cancel out. And then we can go from kilograms to pounds. 1 kilogram is 2.205 pounds, so that the kilograms can cancel out. Okay, so let's just move this down, create some space to work with. What just happened? Let's just put this all the way over there. Okay, so we've taken care of the pound units. Now let's look at the inches cubed unit. We remember that 1 inch is 2.54 centimeters exactly. Remember, now we know what exactly means. It means it has infinite sig figs in this calculation. So we can use that to convert centimeter cubed to inches cubed. 1 inch is 2.54 centimeters. We put centimeters on top so they can cancel out. But this is centimeters cubed. This is just regular centimeters. So we need to cube that whole thing so that the centimeters cubed cancel out. All right, so the only thing that's left here is to punch all of these numbers into our calculator. If you do, let's use a different color, you find that the answer is 0.16296. Let's look at the units. Grams cancel out here, kilograms cancel out here, so we're left with pounds. So pounds per centimeters cubed get canceled out here, and we're left with inches cubed. So inches cubed. But before we can finish, we need to make sure that significant figures match. So here we have 3 significant figures. Here we have infinite number. Remember, 1,000 grams exactly is equal to 1 kilogram. So this is infinite. Here we have 1 kilogram. That's just the whole number. In this example, it's infinite. So we have 1, 2, 3, 4 significant figures. Here we have, remember, 1 inch is 2.54 centimeters exactly. So that's infinite number of significant figures again. So these are all multiplications. So we just use the lowest number of significant figures. So 3. So our answer should be 0.163 pounds per inches cubed, or cubic inches. Okay, so we verified that our units make sense because that's the units that the problem was asking us for the beginning. Now we can think of the last step, verify. We can think of the, there we go. We can think of the magnitude now. The units match, but let's look at the magnitude. We might not know what 4.51 grams per cm cubed might look like, what ballpark our answer should be. So in this case, we can ignore the magnitude for now. Try number 27. It's a little bit more challenging, but try it for yourself. And then when you unpause the video, I'll go over it and just show how we can solve this sort of problem. Okay. In this question, it tells us about an ibuprofen suspension for infants and calculate the recommended dosage for an infant weighing 18 pounds. So let's figure out what information that we're given. Now we have a lot, like we have 100 milligrams of this ibuprofen suspension in 100 milligrams of ibuprofen and 5 mils of suspension. We have 10 milligrams of ibuprofen required for every kilogram of body weight. We have an infant weighing 18 pounds. And they're asking us, so the question is, how many milligrams of suspension should be given? That's a lot of information. So let's write it down. Now, in a situation like these, remember I mentioned that units are a way to give meaning to numbers. But in this example, we have 2 different numbers with masses. We have milligrams that is talking about the amount of ibuprofen, and we have kilograms that's talking about body weight. And that can get confusing because they're both mass, milligrams and kilograms. They're just, it can get confusing. So let's put little descriptors. And sometimes it helps to put descriptors to units. Units are one type of descriptor, but if you have two different units of the same type, it might help to use descriptors. So let's write the things we're given. We're given 100 milligrams, but this mass is of ibuprofen. So let's put a little ibuprofen right there per every 5.0 milliliters of suspension. Let's just put SUSP for suspension. So we're given that. We're also given the recommended dosage is 10 milligrams of what? Of the ibuprofen per every 1 kilogram of body weight. Let's just put body. So that's a little descriptor right there. They also tell us that we have an infant weighing 18 pounds of body weight. A little descriptor right there. And we need to find, let's use a different color. So let's put X for stuff we need to find. Use a different color. X, we need to find how many milliliters of suspension. So that's another descriptor. So this is all the information that we have. This is what we're given, and this is what we need to find. Okay, let's come up with a strategy. Our second step is to come up with a strategy. Now, our answer has milliliter of suspension. We need our answer in milliliter of suspension. So however we set up this problem, that should be the numerator. So here we have milliliter of suspension, but it's in the denominator. So we can just flip that as we set up our problems. So let's just put 5.0 milliliter of suspension divided by 100 milligrams of ibuprofen. All right. But our answer just needs to be milliliter of suspensions, and we don't need any milligram of ibuprofen in our denominator, so we need to get rid of that, change that somehow. And over here, we're given something that can help us convert milligrams of ibuprofen to kilogram of body weight. So we can add that. So let's just multiply by 10 milligrams of ibuprofen per 1 kg of body weight. And because dimensional analysis are helpful, the milligrams of ibuprofen cancel out. So that way we can convert, we can have milliliters of suspension per kilogram of body weight. But again, our answer just needs to be milliliters of suspension. We have kilograms of body weight that we can get rid of. But we have our body weight for the baby in pounds. We know we can convert kilograms to pounds because 1 kilogram is 2.205 pounds. So let's use that. 1 kilogram is 2.205 pounds. So kilograms cancel out. And now we can use the body weight of the infant, 18 pounds of body weight. Pounds cancel out there, body cancels out there. So here we have set up our problem to go to find milliliter of suspension that's needed for this baby without ever thinking too much about the problem. All the other units cancel out nicely. So if we just plug this into our calculator, we get 4.1 milliliters of suspension. There we go. We didn't have to think about significant figures because the answer tells us to assume 2 significant figures. Okay, so we worked the problem out. We got units that make sense for what they're asking us. They're asking us for how many milliliters of suspension, and we found a number that's milliliters of suspension. Let's check whether the answer is correct. So the units are correct. What about the magnitude? Is the size of the answer correct? The value, 4.1 milliliter. Does that make sense? Well, let's look at what we're given. We know that we need 10 milligrams for every 1 kilogram of body weight. And the baby is 18 pounds. A kilogram is roughly 2 pounds, right? When we're checking, we just use rough numbers to make sure that the numbers come out to be around the same ballpark. So if a kilogram is every 2 pounds, then 18 pounds is, roughly 9 kilograms. So if you need 10 milligrams of ibuprofen for 1 kilogram of body weight, for 9 kilograms of body weight, you need about 90 milligrams of ibuprofen. Does that make sense? 9 kilograms, which is about 18 pounds, we'll need about 90 milligrams of ibuprofen. If 100 milligrams of ibuprofen comes from 5 milliliters, then around 90 milligrams should be less than 5 milliliters, right? It should be about 4.5 milliliters of suspension, roughly. Because we need 90 milligrams, not 100. So it should be less than 5 milliliters. And we see that our answer falls somewhere near that ballpark, right? And that's one way to check. Yes, 4.1 milliliters of suspension makes sense. So that's our answer. That's one way to check. I hope that all makes sense. If you have questions, you can always email me. But let's try one more. Let's try number 28 on your own. Pause the video, and when you think you have an answer, unpause, and we'll look at how to solve this one. Okay, this one's similarly tricky, but in a different way. Here we have a mixture of copper spheres and small lead spheres. So let's say copper spheres. We'll use our orange circles. We don't know how many. Lead, we'll use blue spheres. We don't know how many. And their total volume is 427 centimeter cube. And total mass is 4.36 kilograms. So here's a situation where we measured all of the volume, all of the mass, and this is what we get. They give us the density of copper and the density of lead. So those are all the things that we're given. The total volume, the total mass, the density of copper, and the density of lead. And what we need to find is X%. What percentage of spheres are copper? So what percent of the spheres are copper? Is it, 3 out of 5? So 3 out of 5 would be 60%, or some other number. Is it 100%, 0%? They want us to find out what percent of spheres are copper. How do we go about setting up this problem? What is our strategy for this problem? Well, there are a number of ways to solve any mathematical problem. There are many ways to skin a cat. So let's just, for this example, I'm going to use a strategy to figure out, well, let's look at the most obvious answers. Let's figure out whether there's 0% copper and 100% lead, what the mass should be, or vice versa. If it's 100% copper and 0% lead, what those masses should be. So if we have 100% copper, then all of the volume would be copper. So for 100% copper, we have 8.93 grams per centimeter cube. That's the density. And all of the volume, 427 centimeter cube, would be copper. So the mass that we should expect would be 3813.11 grams, or we can convert it to kilogram and use 3 significant figures. That becomes 3.81 kilogram. So if it's 100% copper, then it should be 3.81 kilogram. If it's 0% copper, but 100% lead, PB is for lead, then we have 11.34 grams per centimeter cube times 100% of the volume, so 427 centimeter cube. Centimeter cubes cancel out. We get 484.2.18 grams, or 4.82 kilograms. So if it's 100% lead, 0% copper, it's going to weigh, the mass is going to be 482. The mass that they give us is 436. So, unfortunately, it's somewhere between these two. So it's not 0% and it's not 100%. It's somewhere between those two. Well, we're stuck. How do we figure that out? Well, some percentage, not 100%, of copper, let's say X% of copper, plus, let's say 100 minus X, right? Everything that's not copper, of lead should add up to the total mass, 4.36 kilograms. So whatever percent of copper that we have and whatever percent of lead that we have should add up to 100, the total mass. I use 100 minus X because if copper is 10%, then lead should be 90%, and so on and so forth. And that way we could solve the problem this way. So we forgot the percent sign. The mass of copper, if it's 100%, should be 3.81. So x times x percent times 3.81 kilograms plus 100 minus x percent of the lead, which is 4.82 kilograms, right, should add up to the 4.36 kilograms total. Okay, so here we set up our problems, and all the problem in terms of some unknown that we need to find x. X is the percentage of copper. All right, so from here on out, it's just algebra. You may know that percent just means divide by 100. So let's use that to our advantage. Instead of percent, let's divide this by 100. Divide everything here by 100. But we don't like 100 everywhere, so let's multiply both sides by 100. So we can get rid of the 100 over in the denominator. So that transfers to x times 3.81 kilograms plus 100 minus x times 4.82 kilograms is equal to 436 kilograms. Okay. So this, again, we can expand out this bracket. So 4.81 times x kilograms plus 100 times this would be 482 kilograms minus x times this would be minus 4.82 times x kilograms is equal to 436 kilograms. Let's keep all the x on one side. Let's put all the things that are not x on the other side. So we have 3.81x minus 4.82x gives us minus 1.01x kilograms. We take this onto the other side by subtracting on both sides. So we have 436 kilograms minus 482 kilograms on this side. And that comes out to be, hang on, I read it somewhere, 46, minus 46 kilograms. So minus 1.01x kilograms is equal to minus 46 kilograms. Now they're both have the same units, so that can cancel out nicely. They're both negative signs, so that can cancel out. We just multiply both sides by -1 to cancel that out. So we have 1.01x is equal to 46. X then is equal to 46 divided by 1.01, which gives us two significant figures, right? 46. It gives us about 46. It gives us 46. Remember, that's a percentage, so it'll be 46% as our answer. That's a long walk, but I wanted to go over it with you step by step. We first determined what 0%, what 100% copper and 0% copper would look like, or 100% lead. We set up our problems to add in for x% of copper and 100 minus x% of lead. Should add up to the total. And then from there, it's algebra. I did it step by step to show you how we got to our answer of 46 as x. Now let's verify that the answer makes sense. 46 is about 50%, and the final mass of 4.36 is about halfway between 3.81 and 4.82. So that sort of makes sense. If you have any questions about this, again, please feel free to reach out to me. Try numbers 29 and 30 on your own, and if you have problems with them, send me an email or come to my office hours and we'll go over them in detail for you. But that will bring us to the end of this video and also to the end of this chapter. I will see you in the next chapter. Bye.